Hello everyone, this is the second lecture of week 12. Recall that in the first lecture we had a quick introduction on machine learning, right. So, in fact on supervised learning, a supervised learning problem is a problem where you are given a labeled data set, right. So, where for you have n data points, in each data point you have a feature vector say x1 and the corresponding label of that vector which is y1. For x2 you have y2 dot dot dot, for xn you have yn, right. So, you have in a similar way you will have n feature vectors for in the data, right, and you have an assumption that y and x are connected by a function f, right. So, if you are given a y then x, then you can find y if you know f, right. So, that is what it means when we say there is an assumption that x and y are connected by the function f, okay. And we also have a loss function, okay. So, instead of finding f, if you found f hat, right. So, what is the loss, okay. So, that is given by the loss function L, okay. So, our task is to find f in such a way that the loss function for a given test vector is minimized, okay. So, that is the task that we have, okay. But in case in general if we do not know anything about f, okay, it is very hard to estimate f, okay. So, different methods have some simplifying assumptions, okay. So, there I told you some of the methods which assume that f is linear, okay. So, that means y is linear in x, okay. And there was one method that I mentioned which was a decision tree method, right. So, where it assumes that y is actually a constant in axis parallel rectangles, right. So, there are many such assumptions. So, we are going to consider the simplifying assumption where f is linear, okay, and we are going to assume that the loss is squared loss, okay. So, in the previous lecture we saw that if f is linear then y can be written of this form, x is a vector, a p dimensional vector x1 x2 dot dot xp. So, I am writing it in the superscript because the data point x1 x2 dot dot xn. So, the subscript is the data point, right. So, x1 itself is a vector, okay. So, the corresponding component I am actually writing it on the top as superscript, okay. So, that is why you see the superscript instead of the usual subscript which we have operated in the previous weeks, okay. So, if the loss is squared loss, right. So, to make it precise, f of x is y is actually f of x which is beta naught plus summation beta I x I, okay, where I equal to 1 to p, okay. So, that is y, okay. Now, for f hat of x you can call it y hat if you want, okay. So, that is beta naught hat plus summation I equal to 1 to p beta I hat x I, okay. So, that is an estimation, okay. So, instead of if you want to minimize the squared loss which is L of f of x f hat of x, right, that is norm f of x minus f hat of x which is squared, sorry, which is y minus beta naught hat. So, f of x is y, f hat of x is y hat which is what I am writing beta naught hat minus summation beta I hat x I equal to 1 to p squared, okay. So, note that we are actually given y and x, right. So, but we are given n data points, okay. So, the task that we have is, okay, to minimize summation norm yi minus beta naught hat, sorry yj I will write it, summation, or let this be I and this be j, beta j hat x j j equal to 1 to p squared I equal to 1 to n beta naught hat dot 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 beta p hat. Okay. So, yeah, this is a nice well defined problem, okay, which is called as the method which we call as OLS, right. OLS means ordinary least squares, right. So, if you are asking what OLS does, right, the ordinary least squares problem, it just solves this optimization problem. So, we have a very nice optimization problem, right. So, we have suppose you give a value of beta naught beta 1 dot 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 beta p, okay. So, then we have a loss function for the particular data, okay. So, recall that we have this data tau, right, x1 y1 x2 y2 dot 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 xn yn, okay. So, given a particular value of beta naught hat beta 1 hat dot 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 beta p hat, right. So, you will have the loss function L1, okay. L1 is actually norm of y1 minus beta naught hat minus beta j hat xj xij, yeah, it is j equal to 1 to p the whole squared, right. So, this is the loss function for the first data point for a given beta naught hat to beta j hat. Similarly, you have the loss function for the second data point x2 y2, right. So, that is norm y2 minus beta naught hat minus summation j equal to 1 to p beta j hat xij squared, okay, and so on up to ln summation yn minus beta naught hat minus j equal to 1 to p beta j hat xn, yeah. So, this is x1, I am sorry, x1, x2 and xn, yeah, okay. So, what we are minimizing is the sum of all the losses, okay, and yeah. So, the values of beta naught hat dot 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 beta p hat that you find here, right. So, this is actually what you do in OLS, which is called as the ordinary least squares. So, yeah, the name is very clear because you are actually minimizing the sum of squares, right. So, that is why you get the name least squares, okay. It is called ordinary least squares because, yeah, I mean you have some different kinds of least squares that exist in the literature, okay. So, what you have here is the simplest least squares that you can perform, okay. So, this is you can say the first level machine learning problem that I mean everyone is taught, you can say, in a machine learning class, okay, where you are actually minimizing a simple quadratic problem, okay. So, since it is a quadratic problem, okay, we can actually use all possible methods that we learnt in unconstrained optimization, right. So, if you recall, we spent a lot of time discussing about minimizing quadratic functions, right. So, you can use any of this method to actually find the answer for this quadratic, minimizing a quadratic objective function, right. And of course, I mean, so for quadratic objective function, we also know the answer in a straightforward manner, right. So, I mean, so if you are minimizing half x transpose h x plus b transpose x plus c, right. So, that is something that we discussed for many weeks initially, right. So, of course, we know the answer is minus h inverse b, right. So, in a similar way, if you write this in the form of a matrix, okay. So, I can write this let us say as matrix H for example, okay. So, put this as 1 1 dot 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 1, okay, and here you just write yeah x1 1 x1 2 dot 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 x1 p, x2 1, x2 2 dot 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 x2 p dot 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 xn 1, xn 2 dot 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 xn p, okay, and beta is beta naught, beta 1 dot 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 beta p, okay, and y is y1 y2 dot 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 yn, okay. So, I will write this objective function whatever I have here, okay, sorry, yeah. So, yeah, this objective function whatever I have within this braces, okay, as y minus, okay, beta transpose h, oh, I am sorry, yeah, sorry, it is just y minus h beta, okay, transpose y minus h beta. You should ask why, I mean how does this work, right. So, just look at what is h beta. H beta is, so the first element is beta naught plus beta 1 x1 1 plus beta 2 x1 2 dot 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 beta p x1 p, right. So, one of the elements is the first element of y minus h beta is y1 minus beta naught minus beta 1 x1 1 minus beta 2 x1 2 minus dot 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 beta p x1 p, right. So, you have n such elements, okay. So, if you want to take the norm squared, what do? You transpose this vector and do a dot product with I mean you do a dot product of the vector with itself, right. So, this subjective function that you have, right. So, the task you can actually rewrite it as min over b y minus h b transpose y minus, sorry, y minus h beta transpose y minus h beta. Note that y and h are known to us, right. So, this t is given to us, right. So, capital maybe I will write this as capital Y, sorry. So, capital Y is given to us, capital H we know because I mean I can take the elements of x1 x2 dot dot xn and form this matrix H, right. So, this is just minimizing y minus h beta transpose y minus h beta, okay. So, simplifying this further, you will have minimize y transpose y minus yeah, so beta transpose h transpose h beta, okay. So, that is so and it's plus, I am sorry, yeah, the other one will be y transpose h beta, yeah, sorry, it is 2 y transpose h beta and plus beta transpose h transpose h beta, okay, with respect to beta. So, clearly this is of the form half, yeah, so of course this h could be confusing, maybe I will write it as a if you want, x transpose a x plus b x plus c, right, where c is y transpose y, where of the form half x transpose a x plus b x plus c, where a is h transpose h, right, yes, and b is minus 2 y transpose h and c is y transpose y, okay. And of course, the answer is yeah, the solution is beta hat is minus a inverse b, right, which is minus h transpose h inverse, yeah. So, yeah, you will have a 2, okay, wait, oh, okay, okay. So, since we have a half, this will also be 2, yeah, I will, a is 2 h transpose h, yeah, because you have a half in front, okay. So, I forgot that. So, it is 2 h transpose h, so this will be a half, and here you have a minus 2 y transpose h. So, I mean it will actually be h transpose y because you have a B transpose x here, I am sorry, yeah. So, this will be H transpose y. So, here you have a minus 2 H transpose y, minus half and minus 2 cancel. So, you have H transpose H inverse H transpose y. Okay. So, as simple as that, that is the answer, and of course, I mean, so you can arrive at this answer in as many steps as you want based on the algorithms that we have learnt previously, right. So, I mean, if you have a data set available, okay, so you can just put the data in x1 y1 dot 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 x and yn, okay, construct the matrix H, construct the matrix y, okay, and I mean, if you just apply all the algorithms that we have learnt previously, okay, we will get this particular solution. You can also verify it with H transpose H inverse H y also, okay. So, I mean, this is a much simpler problem. I could have taken this, okay, but I will take a slightly harder problem, okay. So, as I mentioned, this is OLS. There is a method which is, you can say, to an extent similar to this, okay, and that is called as ridge regression, okay. Okay. So, yeah, so we just saw that OLS is minimizing this, right. So, this is OLS, you minimize summation norm squared, right. So, in ridge regression the problem is only slightly different, okay. You are going to minimize the same, okay. So, you are going to minimize the same that is norm summation I equal to 1 to n norm yi minus beta naught hat minus summation beta j hat x j j equal to 1 to p norm squared over beta hat, okay. But not just this, we do this subject to the condition that beta 1 hat squared plus beta 2 hat squared plus dot 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 plus beta p hat squared is less than or equal to some s, okay. So, to explain what this actually means, okay, you are computing the least squares, okay, but what you want is that the sum of squares of the coefficients, right. So, the coefficients are beta 1 hat, beta 2 hat, dot dot beta p hat, right. So, the sum of squares of the coefficients should not exceed certain value, okay. So, this is actually useful, okay, because I mean okay, I can explain a little bit on this bias variance trade off, okay. I mean, I do not want to get deep into machine learning concepts, okay, but I mean, if you have learned something about estimators, okay, in estimation you want to satisfy certain good properties, right. So, you want the estimator to be unbiased, you want the estimator to be yeah, consistent and so on, right. I mean, there are many good properties that you are looking for. So, ordinary least squares is I mean, yeah, so that the estimation that the estimator that you get from ordinary least squares is called the blue estimator, which is best linear and unbiased estimator, right. So, what does that mean? So, there is something called as Gauss-Markov theorem, okay. Gauss-Markov theorem states that among all unbiased estimators, okay, ordinary least squares, the estimator that you get from ordinary least squares, right, has the least variance, okay. So, that is why it is called best, okay, best linear unbiased estimator, that is BLUE, blue, okay. So, if it is so, if it is best, okay, that is if it has so less a variance and it is unbiased and all that, why should we go to some other method like for example ridge regression? So, the issue is that as far as prediction is concerned, okay. So, I mean this ordinary least squares is something that is extensively used in curve fitting, okay. So, yeah, if what you want is curve fitting, yeah, this is best. Any estimation problem would have wanted it, okay. But as far as prediction problems are concerned, okay, what we want is not the least variance, okay. We want something called as minimization of variance plus bias squared, okay. So, take this for granted, I mean you can ask why. Yeah, if I am explaining that, yeah, I mean I may take a few more classes, okay, but that is not required for the course now, okay. So, what we want to minimize is not just the variance, but we want to minimize variance plus bias squared, okay. So, what it means is that let us say it is not your estimator is not unbiased, it has some bias. It may have a low bias, okay, but if the variance is very low, then such estimators are preferred more than the unbiased estimator, okay. So, ridge regression is something which accomplishes this, okay, but for a particular value of s, okay. So, yeah, I mean it is not it does not do it for any possible value of s, okay. So, what this actually does is that it reduces the variance by introducing some bias, okay. So, that is the purpose of ridge regression, okay. I mean if you are not understanding this much, okay, so just take it for granted that this is another method where there is a constraint that is implemented, okay. I mean if you want to read more about ridge regression, yeah, you can, I mean you have many sources, okay, but for this course assume that this is a problem where yeah, I mean we are given a data set, we want to find the coefficients using this method called ridge regression, and ridge regression is just what I have written down on the board here, okay. So, so yeah, now we have actually got constraint optimization problem, okay. So, this is one of the ways of solving the ridge regression problem, okay. There is also an unconstrained way of solving this regression problem, so the ridge regression problem, okay. So, why is that? Because suppose you want to write the Lagrangian of this problem, okay. So, what is the Lagrangian? Lagrangian is L of beta hat comma s, right, no, so beta hat comma mu, yeah, is summation norm yi minus beta naught hat minus summation beta j hat x j squared plus mu into summation beta j hat squared j equal to 1 to p minus s, okay. So, long back in augmented Lagrangian method, right, we saw that, I mean if we know the right value of mu star, okay, then yeah, the constraint problem can be reduced to so yeah, say we know mu star, then yeah, the constraint problem is the same as min of, so yeah, I equal to 1 to n norm yi minus, yeah, the same thing, I should have written plus mu into summation beta j hat squared. Of course, I am removing this s because, yeah, I mean that does not contribute to the optimization problem, right. So, yeah, we have this particular constrained optimization problem, what I am boxing now. Okay. And yeah, so we have another unconstrained optimization problem which I am boxing now. Okay. So, both of them are same if you choose the corresponding value of s and mu. Okay. So, that is you can say that for each value of s that you choose here, okay, you have a corresponding value of mu that you can choose, so that the solutions of both of these problems are the same. Okay. So, yeah, I mean as far as ridge regression is concerned, people either solve the constrained optimization problem or the unconstrained optimization problem. So, both of them are fine, because yeah, I mean for the corresponding values of mu and s, both of them give the same solution. Okay. So, that is the reason why we have two different representations of ridge regression. Okay. So, you can say this is one of the reasons why I took ridge regression as an application, because by introducing one application I wanted to cover as many examples as possible, so as many algorithms as possible, right. So, I can cover both algorithms of constrained optimization as well as algorithms of unconstrained optimization using ridge regression. So, that is the reason I actually picked up this example. Okay. Of course, we cannot cover linear program, that yeah, maybe I should take a different example, but I mean we do not have time. But in the next 3 lectures, okay, what we are going to do is we will take up a data set, okay, so a publicly available data set, and solve the ridge regression problem. That means find the beta vector, beta naught, beta 1 dot 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 beta p, okay, for that particular vector using both constrained optimization algorithms and unconstrained optimization algorithms. Okay. So, yeah, we can complete the course with that. Fine. So, we will yeah, take up a data set and solve the problem in the next lecture. Thank you.